Hi friends, understanding how the machine learning algorithms work and how they make predictions on a given sample is very important for debugging, improving the model performance, and also for explainability. In this second video, we will continue to explore the most useful features of Dtreeviz library, which help us visualize the tree-based algorithms such as decision tree, random forest, and even boosting-based algorithms like XGBoost, CatBoost, etc. So today we are going to train a very simple regression model and visualize the rules and how the predictions are made on individual samples and so many other things. Okay. So the data set, it's about cars. So here we have 4 car attributes: the miles per gallon, the number of cylinders, horsepower, and the weight of the car. So using these 3 variables, we are going to predict the miles per gallon, which is a continuous variable. Okay. So here we have the distribution. The data set is very small. It has only some 392 samples. Okay. So the standard ML stuff, create features and the target variable, define the model, and train the model. Now, for this decision tree, we set max depth of only 3 so that we can visualize the tree. So this tree has a depth of 3, but it is more common to have a much larger tree depth, but it becomes a bit harder to visualize. This is for just demo purpose, right? So we are building a short tree. All right. So once we train the model, all we need to do is we create this visualizer by simply supplying the trained model, the training data along with their names, right? So once we have this visualizer, we can use it to create a number of visuals and explore the rules and so few other things. So the first thing is visualizing the tree itself. Now, on this plot, every point represents one sample. This dataset has 390 samples, right? So there are 390 points. On all these plots, the y-axis represents the target variable, which is miles per gallon. So this value is somewhere between 9 to 40. As we saw here, this value is between 9 to some 46. Okay. So the y-axis is always the target variable with the values. Now, on x-axis, we will see different features chosen by the decision tree at that point. So the model has chosen horsepower to slice the data into 2 bins, right? For example, it choose a value of 190.5 for horsepower to divide the data into 2 buckets. So in the first bucket, we see all these data points. And in the second one, we see the points on the right of this vertical line. Okay. Now these horizontal lines, they represents the average value of the target variable for all those samples in that bin, right? Now, if we were to stop building the tree itself, then the prediction will have only one of the 2 values, either this average value of 30 or maybe this average value of let's say 18, right? So whenever we have a sample, irrespective of how many features the model has, the model simply look at the horsepower. If the value is below 190, it will say, hey, the miles per gallon is around 30. If the value is above 190, the model will say the miles per gallon is around 18, right? So that's how the decision tree works, right? So they take one feature at a time, they find a threshold value, and they divide the data into 2 bins. And for each bin, the predicted value is simply the average value of all the samples happen to be in that bin. Okay. But it doesn't make any sense to have a decision tree of depth only 1. So we continue to build the tree so that we have more continuous values rather than just two values, right, for a regression problem. And then in this plot, we are looking at all these samples. So let's say here we have about some 250 samples, here about 150 samples, right, on the right side of this threshold value. So here we have all those 250 samples, but this time the decision tree, it choose the weight of the car to make a new rule, right? So if the weight is below 2220, it put them into this one bin, which is the data here. And if the value is above, it put all those samples in this bin, right? So for all the samples on the left, the average value is about something like 32. For others, it's something like maybe 25, like that, right? So that's how the decision tree works. We know it. Now, here we have the leaf nodes, right? So the predictions we make comes from one of these leaf nodes, right? So here the number of samples is only one. So this leaf has only one sample and its value is 18. So that's why you will see the value of the sample coincide with the average value of that leaf. So whereas here we have about 94 samples. This is how they are distributed. Now this time we don't have a feature, right? Because we are not going to make any cut. So this is the leaf. These are all the 94 samples and the average value of all those samples is 32, right? And same explanation for all these. Now in an ideal scenario, what we want is for a given leaf, we want this distribution to be very narrow. Like for example, something like this. So here we have 22 samples. All those samples are close to their average value. Okay. All right. Then we can visualize the tree. I mean, if you like left to right, we can set the orientation. It's the same plot, but viewed from left to right. And then if we disable fancy, for all the nodes except for the leaves, it will show the rules rather than this raw data. So for example, the first rule, it made it this horsepower 190.5 and then the weight it 2219.50. These two rules we have seen here, right? These are the two rules. All right. And then again, as I mentioned, the tree depth will be large for a more complex data set. But if we want to look at particular layers, we can do that. For example, here, let's say if I do this 1 to 2, so we are looking at the first layer and the second layer. So the layer, this one, let's say 0. So this is first layer, second layer. Let's understand the leaf nodes from where the final predictions come from. Okay, the tree we built has 8 leaf nodes and these are their indexes or IDs. Okay, so this is the tree we built. It has 1, 2, 3, 4, 5, 6, 7, 8 leaves. And the IDs goes like this: 0, 1, 2, 3 and 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So it is 3, 4, 6, 7, 10, 11, 13 and 14, I guess. Yeah. All right. So first we are looking at the number of samples in each leaf. Nothing interesting, except the fact that this leaf has only one sample. And then here we are looking at the target variable distribution within each leaf node. So the third leaf, which has only one sample, so its average value equal to the, its value equal to the average value, which is indicated by this black vertical line. Now, if you look at the leaf ID 4, which has about 92 samples and the target value is distributed like this. So the average value is about 32-ish and the value spread between 20 to 45, right? Now, ideally, we would like to have a distribution like this, right? Where our sample's target value is close to its average value. The reason is the way decision tree works is when we have a new sample, it passed through one of these paths and ended up in one of these leaves. Now, if the sample ended up in a leaf like this, then its prediction would be equal to the average value of all these samples ended up in it during the training period, right? So here it has 22 leaves and their average value is 17.85. So our new sample, if it goes through, let's say some path like this, that prediction would be 17.85. That looks reasonable because all of the samples belonging to this leaf, they have a very similar target value. So they are most likely similar to each other, those samples. Whereas if a sample ended up here, now the prediction would be 32, but you can see a quite wide spread, right? Which is what we are seeing here, right? Of course, this tree depth is only 3. If we further let the tree grow, then we will have more separation. So each leaf will have its sample average value. The spread will be narrow, but that can come at the expense of overfitting the tree. Okay, so whenever we build a decision tree, a plot like this will help us understand how many samples we have in those leaf nodes and how the distribution of the target variable in those nodes, right? So as I mentioned, ideally we would like to have something like this or this. Okay, now we can look at the node statistics as well. So simply give the node number and it will give you like pandas data frame summary value for each features. Okay, and then we can also measure this leaf purity. So in the case of classification, this would be Gini value, but in the case of regression, this is the mean of the absolute error. So again, for this one, the value is 0 because the mean and the sample value is equal because we have only one sample. But for these trees, these leaves, we have a large error, right? Because the spread is quite large. Whereas for these two, 11 and 14, the spread is narrow, close to its average value. So the error is also less. Okay. Now, one of the advantages of the decision tree or any tree-based algorithms is we can look at what path it took and what rules it has applied, right? So decision tree is basically a collection of rules, right? Whenever we have a sample, some of those rules are applied or it's the path, right? So let's take one of the samples randomly. Okay, this sample happened to have these 3 feature values, and then we can look at the path it took. Now this is exactly the same tree we saw before, but the additional information is in each of these nodes, we have the feature value indicated. For example, this horsepower 198, so which is here. So it is slightly higher than this threshold rule. Okay. And then because it is slightly higher, the model or this sample took this path. It took this right path. And then here it has a horsepower value of 198. And for this node, the threshold is 284. So it's on the left side. So it took this path and it went on like this. And finally, this sample ended up in this leaf, which has an average value of 20. So our predicted value would be 20. Okay. Now, if we want to look at only this path without cluttering with these not used paths, we can do that. We can simply say just show path is equal to true. So that's what we are seeing here. Now, if you want to have only look at the rules, these are the rules applied. So there are 3 rules, but 2 rules are simply based on this horsepower value. So here we have two values. So what happened is, first the model checked if the horsepower, because this sample has a horsepower value above 190.5, so that's the first rule. So is the horsepower value above 190.5? And then in the next layer, it checked if the horsepower value is below 284.5. So below 284.5. And then finally, it checked if the weight is below 3431. So these are the three rules applied to this particular sample, or this particular sample took that path. Okay. Now we can also look at the feature importance. So for this particular sample, this horsepower dominated, followed by the weight, but it has a very negligible contribution. Okay. Now let's look at a different sample. Okay. These are its values. Now this tree obviously took a different path, and it ended up in this leaf. Interestingly, this is the only one which used the number of cylinders feature in this tree depth of only 3. Okay. So these are the three rules applied. Now, if you look at the feature importance for this particular sample, in addition to horsepower, we also have the weight and the number of cylinders. Okay. So with this type of exploration, we not only have this feature importance at the global level, but whenever we have a sample with some prediction, we want to understand why the predictions are in a way, what features have contributed to it. This library can help us understand all those things, right? The paths it took and the features contributed to making that prediction. Okay. And finally, we can also look at, let's understand how the feature space is partitioned. Okay. So we simply call this function feature space, and we can indicate one or two R variables, right? So here we are looking at only one variable, which is this horsepower, right? So horsepower value have a value between 450 to 450. And then on y-axis, we have the target variables miles per gallon. Going back to our tree, it has made two rules on horsepower. The first one is at a value of 190 and the second one at 284. So here we have the first rule at 190 and another rule at this 284. So all the samples belonging to this bucket will have an average value of around 28, right? But of course, we are not partitioning this just based on one feature. So we have other features are also taken into account when partitioning, right? So here we are looking at two features, okay? Horsepower as well as the weight. So we just saw the horsepower, the two rules. So these are those two rules, and we have more rules based on the weight. So the vertical lines, they indicate the partitioning based on the weight. Now this color indicates the target variable value, right? So these ones have high mileage because they have the weight of the car is low and also the horsepower is low. So the blue indicates higher value, the light green indicates low values for our target variable. Okay. And finally, we can also create this these three-dimensional diagrams where we can visualize the target variable along with two feature variables. So here we are looking at horsepower and weight and the target variable here. Okay. So when we have low horsepower and also low weight, which is in this region, right? So the weight, it's a bit little confusing. So the axis is from here to here, it's from top to bottom. So both the features have a low value in this region. Okay, in this region, that's where we have the highest mileage. Okay, so here we can see how the feature space is partitioned into different planes and for each plane, what is the average value of our target variable. Okay. Yeah, so in this video, we saw how we can make use of this Dtreeviz library to understand how these tree-based algorithms make the decision rules, how the feature space is partitioned, and which path the individual samples took, and the feature importance for individual samples. Okay, that's all for this video. Thank you very much.